progress.
Hello, audible.
Yes, sir.
Good morning, all of you.
Good morning, sir.
Hello. Just a minute. How to share screen? The host. Make me host. I am not able to share my screen.
सॉरी
होस्ट बनाओ मुझे.
ओके ओके ओके
Yes, please. So let us we start. Okay, first we are continue this alternator chapter. Up to which question we reach? 8. Sixth seventh we have also complete. Now same question was asked. We have to solve that also. Already it is up to some steps we have solved. Then you refer my solutions which I have shared. Okay, for latest questions which was asked in your ETO exam. Now come to the eighth. Describe with the aid of a simple sketch the arrangement of three-phase winding of an alternator show neutral point. Then why most ships neutral point is insulated and why in some installation neutral point is earthed. So here just he is asking you have to draw. Okay, this eighth question is just part A. In part A, there is no part A and part B, correct? Yeah, is part A, part B, C also. Okay. He said that just you have to draw the three-phase winding of alternator, which is star connected. And you show the neutral point. So see, this is the three-phase winding of alternator. Just you draw like this. Then these are the three-phase winding. Okay, line 1, line 2, line 3, or RYB. Here you show the phase voltage, okay, across each winding, phase. Here between this, we have a line voltage, okay. Then here we show the current, okay. So line phase current equals to line current in star, okay. Here is the phase or winding current, okay. This is the phase current. Now this is your neutral point. You can show this is your neutral point, okay. Sorry. This is the neutral point which is in grounded system. Now you know grounded and ungrounded, okay, or it is called, there is a earthed or neutral. We can write here neutral, earthed or neutral grounded system. Okay, so here in neutral earthed system and neutral isolated or insulated system. So why in neutral earth system, this neutral point, you can separately draw here, okay. This here in neutral earth system, this star point, okay. This star point is solidly or directly connect to the earth, okay, journal mass of earth, grounded, okay, correct. But at each voltage level, either it is a three-phase transformer, three-phase alternator, at every voltage level. But here in neutral isolated system, we kept it isolated, or we not connect with the ground, okay. correct? So there is a advantage and disadvantage of the system. In this chapter, there is a power system, power distribution system. There is a numerical also on that neutral earth system. Okay, line 1, line 2, line 3 is there. Here is also. So there is a advantage of earth system. So here you write the advantage of neutral earth system. You know, first is here in earth distribution system, you know, here is a zero potential at ground level. Zero potential, correct? This zero ground potential now means it appears at here. So here, if this is connected to here, means this neutral point has zero potential. Now, with respect to this neutral and here line across this is a phase voltage. Okay. So in this system, if we check the voltage between, see, suppose this is the ground. So here and this line, between line, any line and ground, this potential between line and ground, it is a phase voltage. And this is equals to line voltage by √3. Okay. But in isolated system, if you check the potential between any line and ground, it will be line voltage. This is the major difference. So now here less insulation is required per each winding, but here it is designed for a line voltage. Okay. Now suppose in case of a earth fault occurs, single line to earth fault in earth system. So suppose this fault occurs, any line can become a ground like this. Then you know, suppose L3 is come in contact with the ground, or it is called as a line to earth fault. Line to in case of line to ground fault, or it is called as a earth fault. Okay, correct. So you know, it make a closed path nearest to your neutral grounded system like this. Okay, then what happens? The current, very high current, is passed through the winding which is become a ground like this. So this is your fault current path. Okay, this is your fault current. Through this neutral, very high current is passed. So it is called as it is a current path, fault current. It is a fault current. So see, the current through this line means I3 is become equals to fault current, neutral. It is earth fault current. It is similar to short circuit current, very high current. That means this winding may be damaged. Okay. That's why we prevent this earth fault protection we provide. Okay. Now, but you know, this two current in this remaining two phases, I1 and I2, okay, they become a zero. Okay. But suppose if we discuss here in isolated system, this same scenario, suppose one line is come in contact with ground, means it is earth fault. Okay, then this not make any circuit closed path. Now you know there is a this by put neutral, na, we make a ground resistance less than 1 ohm. Okay, but here it is a, because ground also has some resistance. Okay, then there is a no current is path. No current will flow through this. Okay. Sorry. No current will pass through this line. Okay. Even this I3 become 0. But these two remaining two phase are continue carry a load current. Sorry, I1 and I2 will continue supply to the load. That means these two phase are available for supply. Here is no blank out. But here, due to this fault, okay, now current 0 means means power is not available. But here we can easily provide the in neutral earth system, we easily provide the earth fault protection. How? Very simple. See, what we do, this star point is connected to ground, no? Here. Okay. Now, suppose here there is a breaker, you know, circuit breaker, okay, like this. So it is a 3 ACB, here circuit breaker. There is a trip coil of this breaker. Now we provide a neutral CT here, just, and it is connected to this trip coil, okay, just. So in case of, if there is no earth fault, this all three phase carry the load, they feed the load here. See, this is the load in normal case, and it is a balanced system, means in all three phase there is a same current. It means there is a no current is passed through the neutral in normal case. But if abnormal condition, suppose earth fault is occurs, then very high current pass through the neutral. It means there is a response in CT secondary. Then this current is passed to trip coil of breaker. Okay, it is energized, it trip the breaker. Okay, so this is the your simple earth fault protection. SGB, okay, here circuit breaker. But here it is difficult to protect protection for in isolated system. Here actually we use, how we provide the earth fault protection in isolated system, we use a DC current injection relay here. Okay, DC current injection relay we provide, okay, correct, and it just give the alarm. So we detect the fault only, okay, then we separate this particular phase which is become ground, we detect and we identify the fault, we clear the fault, then we continue. Okay, so here why this is the advantage disadvantage of, now in earth system the person we get a electric shock, but here if suppose a person okay, suppose a person is come in contact with line, then there is no current is flow, because it is due to high resistance, okay, of ground and the body of the person. Okay, no leakage current is passed. But in case of, suppose there is a high potential, see, in case, because here is it is a zero potential, 0 volt. So here is a 0 potential, and here it is a line potential, like it 440 volt. Okay, so no current is passed, then but there is a flash over, chances of flash over flows in case of high voltage system, when suppose 11 kV, in case of 6.6 kV. So due to high potential and here is a zero potential, there is a flashover. Flashover means arcing. Then direct burn injury will occur. That's why now he is asking now why in some case we have neutral is earth and in some neutral is isolated. So mostly on board we have to, this electrical system is isolated in LT, low voltage system, LV system, the LT or LV, okay. Neutral is kept isolated, but in HV system we have grounding through NER. Now other method, hello. Now there is another, suppose in HT system like 3.3 kV or 6.6 kV or 11 kV, yeah, system, we do the grounding through NER. NER means neutral earth resistance, okay. We connect a series resistance or series reactor in the, we do the grounding through resistance. Then it provide a high resistance path. Suppose in case now fault is occurred, then it make a again circuit. Now to limit this fault current up to full load current, because this winding is designed for a full load current carrying. Because when load is connected, normal case, there is a continuous current carrying capacity is there, no? Okay, so means these coils are designed or windings are designed to carry the full load current continuously. But in case of earth fault occurs, then very high current is passed. So to limit this current, we put a resistance. So it is do resistance through NER. Okay. Ninth, what is the significance of root mean square value? Already we discussed in first chapter, and this from factor, peak factor, numerical also. Now there is a this ninth B second question. It is this lot of times is asked in ETO exams. Okay. So very simply you can solve this. It is your ninth B, yeah. Here we can write. Okay, so this is the ninth B. So when we solve this, you just total load is there 8,000 kilowatt at 0.8 power factor, supplied by two alternators running in parallel. One alternator load is given kilowatt and 0.9 power factor. Now he is asking kVA rating of other machine. Again very simple. Suppose here these two alternators, you draw the sketch. These are running in parallel and connected to a common bus bar. Okay. Okay. This load is connected. So this total load 8,000 kilowatt at 0.9 lagging power factor. Sorry, 8.8. 0.8 power factor. Now here, this is suppose alternator 1, this is alternator 2. It is here 6,000 kilowatt at 0.9 power factor. Now is asking what is the kVA rating, not a kilowatt load. It is a kVA rating of this alternator 2. Okay. So here, very simple way. If it it's called the loads, load, then their parameters. So your total load, then load shear on load on alternator A, load on alternator 2. So here loads and their parameters. So C, load in kilowatt, then their power factor. Okay, power factor means cos phi. Okay, then you can calculate a kVA load in kVA. Okay, kVA load, kilowatt load, kVA load. Okay, correct. So see here, total load in kilowatt, it is 8,000. Total load, their power factor is 0.8. Then kVA we can calculate na kilowatt by power factor. So it becomes 8,000. Yeah, it comes 10. Okay, so it is come 10,000 kVA. Okay, sorry, 10,000. So this total load is come 10,000 kVA. Now alternator 1 has a 6,000 kilowatt share, power factor is 0.9. Now we can calculate the kVA load on alternator 2. Again it is 6,000 divided by 0.9. Okay, so it comes 8,000.
No, sir. 6.67.
This is 0.9. Na?
666.67.
Okay. It comes correct. 4 times 6.67. 1, 2, 3, 4.67. Okay. Then we can calculate a load shared on machine equals to total minus shared by machine. So it is, if we calculate in kilowatt, it is comes
केवीए माइनस करेंगे तो नहीं आएगा सर, रिमेनिंग केवीए उसके ऊपर दूसरे के ऊपर.
Yes, kVA we can also do na. You can calculate in kilowatt and kVA, because sometime na power here in it is not asked, but if suppose they ask the power factor too also.
हाँ, पावर फैक्टर तो लिए चाहिए सर. अगर केवीए भी टोटल जैसे 1 केवीए का 2 केवीए का ऐड करके इक्वल हो जाता
यार
होगा.
राइटिंग इन बोथ ना, बोथ केस में हम दोनों चीज में बताएंगे, किलोवाट एंड केवीए. ओके, देन वी कैन डिटरमाइन द पावर फैक्टर आल्सो. So see here, it comes 2 kilowatt. Okay, sorry, 2,000 kilowatt, And kVA load also we can find. So this is the kilowatt load on, you can write kilowatt load on alternator 2. Now kVA load on this equals to again total kVA minus shared by this machine 1. Okay. It comes 4 times 3 into 3 kVA. So this is the kVA rating, kVA rating of machine or alternator 2. Okay. Now if suppose they ask the power factor, here it is not asked, but cos phi 2 will be your 2000 divided by 3333. 0.6 lagging. Okay. So this is the question. But sometimes they ask the kilowatt and kVAR load also. Then we use a 10 phi. Okay. If they ask the kVAR also. Okay. Now we can calculate a kVA rating here also. Okay, dear. Now next, here again same question. Explain the significance of root mean square value. Same question. Now we are load sharing 10 megavolt ampere, 10 MVA, 3-phase alternator operating in parallel, supply at a 0.8 power factor, load, lagging load of this 15 kVA is the total load. Okay. If suppose output of one machine is 8 MVA, calculate output of second and power factor of second. So here we require both MVA and MVAR. Or now we can calculate kilowatt and megawatt and megavolt ampere, then power factors too also. It is also easy, 10B.
Sir, this in the previous question, this kVA rating of the alternator will be the same as kVA of the kVA load of the on alternator 2.
kVA rating of alternator 2 is same as a kVA load.
Okay,
slightly higher than we decide the size. But how we know? Actually, it is like. But here we cannot say na what is your like there was one derating or diversity factor they apply. Okay, so we write this only actual reading, or you can write margin. It is we can take or it is available in market. What is the rating nearest close to that? Okay, like it is maybe.
Okay, sir.
Yeah. Now, the same question is this, okay? 2 alternators. Suppose here alternator 1, 2. Okay. This is both are operating in parallel. This total load. The total load is given 15 mega volt ampere at 0.8 power factor. Okay. And load on alternator 1. See this, or machine 1 we can say. This is machine 2. So here this load is 8 mega volt ampere at 0.9 lagging power factor. Okay. Lagging power factor. Correct. Then he's asking what is the output of second. Now he is not asked what is in MV or kilowatt, but he is asking power factor too. Then we define in both MV and megawatt. Okay. So here instead of kilowatt and kVA, we use the megawatt and mega volt ampere, MVA and megawatt. Okay. So see again same your loads and their parameters, loads total, then your shared by alternator or machine 1 and alternator 2. Okay, this is alternator 1 and 2. Total load is now total load in megawatt, it is given mega volt ampere. Then their power factor means cos phi. Okay. Then we can calculate their megawatt. Megawatt load. kVA, MVA load. Okay. So see here, the total load is 15. Okay. Now if each capacity is 10 flow, this is the 10 mega volt ampere capacity. This is also 10 mega volt ampere capacity. How much they can share jointly? Okay, combinedly 20 full load rating capacity of the system, but actual load is 15 MVA. Okay, so your actual load is 15 MVA with power factor 0.8. Now in watt, okay, megawatt is your MVA load into power factor. So it comes 15 into 0.8, 12 megawatt. 12 megawatt. Now machine it is 8, power factor is 0.9. Then megawatt load, it is 8 by 0.9 also, multiple point. So this load on this, it is 8 into 0.9 also. Okay, so here
7.2.
Very good, 7.2 megawatt. Then alternator 2 we can calculate na. Total minus shared by machine Okay, so it comes 7 megavolt ampere. Then kilowatt 12 minus 0.7, 4.8. 4.8. Okay, how it comes? 12 minus 7.2 if we do. Okay, this much of 12.72, we get a 4.8 megawatt. Now therefore power factor, power factor of machine 2 is again megawatt divided by megavolt ampere. Okay, 7.
0.68.
0.68. 6 legs. Okay. Why is a synchronous motor is not self-start? What are the various ways which we make it self-start? A 500 volt single phase synchronous motor give a net output mechanical power. Operates at 0.9 power factor lagging. Its effective resistance is 0.8 in armature resistance. The iron and friction losses are this. Excitation loss is this. Calculate the armature current and commercial efficiency. Okay, so it is based on the equivalent circuit, your power flow diagram of the synchronous machine like motor. Okay, now already I shared some notes on synchronous machine. There is a explain the working principle, because when we connect the synchronous motor to three-phase supply, the poles are created on the stator. Same number of poles are created on rotor also. Then they are magnetically coupled. So here there is a net torque is, because now based on the frequency of AC supply, this phase sequence like resultant is will shift it is rotate like in three-phase induction motor. Okay, so your net torque will come 0, then it's not rotate. So to make a self-start, we require an initial torque, that is by pony induction motor, or other method is by damper winding to make a self-start of the motor. Okay, so there is a 2 method to make it self-start. Now this numerical, It is 11th part B, okay? Yeah, you write the power. Before this, we start this question. You have to understand the power stages or power flow diagram in three-phase synchronous motor or synchronous machine, synchronous motor. Okay, first is power input to stator. Power input to stator or stator input. That is, if we take a per phase values, it is 3 into phase voltage, phase current, armature current, okay? Because load current equals to armature current in motor. Then power factor also. So this is you have to draw the equivalent circuit also, machine. I will explain. This is your induced voltage. Then the armature resistance is there. Synchronous reactance is there in equivalent circuit. Okay. Oh. Okay, then this is your, we represent the load. It is a mechanical load, okay, on motor. Correct? No, here. In case of motor, no, we give the supply here, sorry. Here you apply the voltage to motor.
सर ये जो पावर इनपुट रहेगा लाइन वोल्टेज लाइन करंट ये वाला नहीं रहेगा सर थ्री फेस रूट थ्री
Actually, in equivalent circuit, this all parameter are per phase. That's why we take a phase values. If you take a three phase, then you root 3 VL, IL cos phi you can also take, okay? Not issue. So here we apply the V, then it carry the load current or line current. Here it is a armature current, okay? Then here back EMF is induced. In alternator it is a induced EMF, E. And here in alternator this angle is positive, but in case of synchronous motor this angle is negative, del, okay? Load angle. So here, see this power input, if we give here three phase AC, then this is this. After this, okay, then from this stator input, what is the loss first occurs? There is a armature copper loss in armature winding. Armature copper loss is, okay, due to current. So this losses are armature current into armature resistance, but 3 times for 3 phase, okay? These are per phase current, per phase resistance, okay? Then remaining power is, it is a gross mechanical power developed then in the ear gap, okay? Or it is called ear gap. Mechanical power develop in ear gap. sorry. In here case, or it is called as a rotor input. So please, this is the mechanical power. How we can define? With back EMF, actually, or induced EMF. This is into IA armature current, then cos of alpha minus phi. I think here load angle is alpha, is take alpha. Okay. Then here, after this, no, sorry. What is the loss is occurs? Friction, windage, rotational loss. What it comes? Rotational losses. Okay. Rotational losses. Rotational losses are include iron loss, means mechanical plus magnetic. Excitation and friction. This is okay. Iron plus excitation plus friction loss. Then remaining is we get a output power. Output. Okay. Or it is the shaft output. Okay. In case of motors. Correct. So here, first of all, this is 500 volt, means here it is a line voltage is given. VL is 500 volt. So first you calculate in the phase values if required. Then it is a single phase only. The motor is single phase, means this voltage is also single phase. Correct? So here the motor is single phase. Then see, these things are not come here. Okay, only single phase input of VI cos phi. Okay. So here output of mechanical power. So net mechanical output means here this power is given. Hello. This power is given, that is 7.46 kilowatt. Net output. Because motor has a mechanical output, na? Net output is given. Operate at 0.9 power factor. Here power factor cos phi is also given. 0.9. Effective resistance RA is also given. This is 0.8. Iron and friction loss is 500 watt. Here iron loss only. Iron. Actually we write this no. This rotational loss is iron loss, means core loss, plus your excitation loss plus friction loss. Okay. It is a sum of this all three. Okay. Now here, you know, he said that iron and friction both combinedly. Again, it is we have to interchange. Iron plus friction is combinedly mentioned. Loss plus excitation. So combinedly this iron and friction is given 500 watt plus excitation loss are 800 watt. Okay, so we can calculate 5 plus 8. 500 plus 800, 1300. It means it is 1.3 kilowatt. Okay. So now this 7.5 plus 1.3 kilowatt. Here it comes gross mechanical power developed is 7.46 plus 1.3. Okay. So what is the gross mechanical power? 8.76 kilowatt. Now here this loss is given, so it is a single phase only. Now so here 3 will not come. Okay. So this we can calculate, my dear. Current is not given. 500 single phase to the next could operate at pointed lagging power. Effective resistance is given. Now calculate the armature current and commercial efficiency. When armature current, then only we can calculate the loss. Okay. So how we calculate the armature current? So here to calculate the armature current, motor input. Motor input equals to VI cos phi. Okay. And armature copper losses. IA square RA for single phase. Then gross, we can calculate the mechanical power. Gross mechanical power. See, first is from bottom. Hello. If we come from here to here, okay, then we get this. We can also calculate from top to downside. It is upside, downside. Okay. So this motor input means V armature current. Here it is armature current into cos phi minus armature loss, armature copper loss. Okay. So this relation will give you 8.76 into kilowatt into 1000. No? Then we get a kilowatt only. Okay. So just you put the values. V is 500. Just a minute. Now it is interesting. Okay. Please remember, in this question, actually, this is the step is tough only. You to calculate armature current, you should apply this thing. Okay. So here V is, if we write this equation continue, therefore, for armature current, we can continue, na, like, hello, it is 500 IA, cos phi is 0.9, minus IA square, R is 0.8, equals to 8760. Okay, what? So now we can write, na, this become a quadratic equation. Hello, 0.8 IA square, sorry. 0.8 IA square minus, this is minus, plus 500 IA, 500 into 9. So this become 500 into 0.9. It comes 450. It comes 450 IA. And this side, if we take this also, it comes 8760 equals to 0. Or you change the sign, then it become 0.8 IA square minus 450 IA plus 8760. Then by solving above quadratic equation, we get this value of IA. See, in calculator, you go to in equations, you select for, again you go for a degree, that is a second. A is 0.8, B is minus 450, and C is 876. No? $8,760. My dear, this value is come 542.3. There is a two values will come, na, x1, x2. So second is 20. 19. Okay.
सर एक डाउट है,
हाँ,
यहाँ पे अपने मोटर पावर इनपुट के लिए V फेज इंटू आर्मेचर करंट इंटू कॉस फेज लिखा है, बट आपने यहाँ पे लाइन करंट का वैल्यू लिया है.
actually it is a series circuit, na, in armature, sorry, synchronous machine, armature current equals to line current, they are same, na. Sorry, see here both are equal, na, in this circuit. Okay, because line,
Okay sir.
IA equals to IL. Okay, now which value we take? Correct value is here, it is taking it from root mean square value. Okay, so here two values are come, correct now? So here this is the higher value, okay? it is wrong. Okay, we assume this will be the correct. Okay, for this. This armature current is correct. Okay. Here we consider this value. So here the armature current. Okay, therefore armature current IA is 2.19. Because you can check this. If why we consider only 20.19 ampere? Because if you multiply this 500 into 20.19 into 0.9 power factor, VIA cos pi. Okay, it should give you 87. Sorry, your input now. What is the motor input? Oh, what value it gives? Just we check. Motor input. Now we can calculate. Hello, here we calculate motor input. Okay, motor input. So this motor input equals to this. Sorry, not it. We cancel this. Now just 500 into 20.19 into 0.9. Okay, so it is comes 900 085.5 kilowatt. So it is an order, because now you see the block, this flow diagram. Here it is come 8,000. Then if you add some 9,000 is okay. But if you take a higher current, this 500, what is the value? Second value is come, that is 500. Then it is very high, na? Okay. So your true value for this case is 20 ampere. Then it is okay. Now commercial efficiency. So here there is a two part now of this question. First part is asking armature current. Second part is asking commercial efficiency. Hence your output by input into 100. Output, motor output is 740 divided by input is 9085.5. Six zero. 82%. 108 means 2 we can add, or 11. There was 80.21. Okay. This much only. Okay, dear. Simple question. Single phase only. They give, so nothing is a. Okay, dear. Please you take this screenshot. You can take from your this mobile. Hello. Or I will put this in. Okay. Just. But every time I have to save this. Copy. We use a Telegram, Oh, great. Okay, dear, I put in your group also. Okay, excellent. Now, if required, I will sometime I put the solution also. Okay, not issue. But it is quite silent, and number of question also more will be covered. Okay, dear.
सर ये इसका जो साइंटिफिक कैलकुलेटर में इसमें किसमें जा इक्वेशन में जाके अननोन 2 में जाएंगे ना सर?
नहीं, अननोन के बाद अगेन आप वो मोड प्रेस कीजिए. अननोन वो साइमल्टेनियस इक्वेशन के लिए रहता है, बट जब पावर में आ जाती है ना, तो यू अगेन प्रेस द मोड, देन इट इज आस्किंग योर डिग्री. It is a second degree, third degree for cubic equation. Okay. Now, this again there is a synchronous motor principle. Find the synchronous impedance reactance of the alternator in which a given field current produce an armature current is given this. So here is some this question is based on your which I called OCC SCC test. So he is asking your value of synchronous impedance. It is a very important question when we discuss your OCC and SCC and voltage regulation. So here it is given short circuit current, armature short circuit current, and armature your EMF, open circuit voltage. The armature resistance is this. Then to what induced voltage must be alternator to be excited. Now he is asking deliver a load of 100. Now this ampere load current is rated load current is 100 ampere for this 0.8 power factor. Terminal voltage is this. So he is asking induced voltage E. So your phasor diagram, we use that to calculate. Okay, you got it. This what is this question? Actually, very important question. This 12th is. Now here again, here it is not mentioned. It is a single phase or three phase. By default, it is a three phase you consider. Okay. This 11th and this 12th question was very excellent. Okay. अभी तक वीडियो में नहीं आए, but they can ask. It is 12th B. Okay. Will be okay. He is asking you calculate a synchronous impedance. That is, from this open circuit voltage to short circuit armature current. Okay, this. Okay, so for here actually it is given two characteristics, like when we perform an open circuit and short circuit test. Okay, so there is a OCC and SCC we draw. like in voltage regulation, impedance method of voltage regulation. Okay, synchronous impedance method. Okay, so you get their steps now how we find the voltage regulation by synchronous impedance method. You can now I tell. वो उस दिन अधूरा भी रह गया था. Okay, so today we will explain the complete process steps. Okay, so here this is suppose your graph paper here. First I write the steps steps of what it is the synchronous impedance, or it is Z as impedance method. Synchronous impedance method or indirect method of voltage regulation, to determination of voltage regulation. Okay, how we calculate this? Very simple steps. First of all, find RA, means armature resistance, by measurement of armature resistance winding. So here it is given. What is the armature resistance? Armature current short circuit. Armature resistance is 0.1 ohm. It is given, my dear. Okay. Just a minute. Yes. So this is the your, and see this always equivalent data are given per phase values. Okay, so it is ohm per phase. Now you have to calculate second steps. Draw OCC, means open circuit characteristics, and SCC. See, this is the steps of your to find the voltage regulation by indirect method, that is MMF or synchronous impedance method. So we draw this from open circuit test, open circuit and short circuit, OC and SC. Open circuit and short circuit test data. So see, here is data is given. We have to run the machine. Okay. So first is open circuit characteristics is what? Actually, your open circuit characteristics is like this way. Get saturated. So this is your OCC. Okay. It is what actually? It is nothing but it is your open circuit voltage. Please move that. Someone. Open circuit voltage to versus field current. So here on this axis. Hello. Someone is speaker is on. Please mute. And here we take a open circuit voltage. Okay. On this axis we take a short circuit current. ISC. Actually it is armature current under short circuit. Okay. So we get now when we draw the from short circuit data, we draw SCC, short circuit characteristics. It is like this. So it is a straight line we get. Okay. Now he said that we consider now third steps. You have to consider a particular field current, IF, value of IF, value, any, and calculate, or from the graph you have to calculate the open circuit voltage and short circuit current corresponding to IF, particular value. So from this graph now there is a different values of IF, okay, and then corresponding to this there is a open terminal voltage and short circuit current, okay. So he said that you consider any particular value. Suppose we consider this is the IF value, okay. For this intersect your HCC, short circuit current, and for the same value of current there is a open terminal voltage. So let us, this is your OC and this is your ISC corresponding to this field current, okay. These are the values of corresponding to this field current, particular value, okay. Now, therefore, when you get this, now we said find ZS, synchronous impedance, very simple, open terminal voltage by short circuit current, and it is constant. Either you consider here this value, okay. So corresponding to this also, this ratio will come always constant. Okay, it will give the constant value. That's why we have find, okay, this. Okay, here. So in same way, we have to calculate here also. Now you know, actually this voltage here, the generated EMF of 50 volt on open circuit voltage, and you know your three-phase alternator is connected in star. So for star connection, line voltage equals to line current equals to phase current. Okay, so here this IA is given please note 2000 ampere. It is the per phase only, okay, because phase current equals to line current. But here this voltage open terminal voltage, actually it is given ISC. But your open terminal voltage is, that is given 500 volt. It is a line voltage because your voltmeter is connected between two phases. Correct now? Just I draw this diagram here. So if see your this is a three-phase winding of your armature winding of your alternator, okay. When this is your diagram, okay. Suppose you're running on open terminal voltage, so we measure the voltage here, correct, between the lines. And when we short this, then we measure we put a emitter also here. Now in star connection, here this line phase current equals to line current, correct? When it is short, then voltage becomes 0, current becomes short circuit. So current is okay, phase current here, okay. This actually it is not an armature current, it is a short circuit current, okay. Okay, and always I want to notice, please you always sit with along with a notebook, pen and calculator. and parallelly I give the lot of time, you can note down the things, okay? So it is a line voltage actually. So now we calculate a per phase value is 50 by root 3. So please, this voltage need to divide by root 3. It comes 28.87 volt per phase, okay? तो इसको ठीक तरह से लिखते हैं. We get this much volts per phase. Now phase values, so here we take a phase values. So I am doing calculation also, okay? So this is your hello 28.87 divided by short circuit current is 2000 ampere. Sorry, 200 ampere. What is the this impedance will come? My dear, it comes 0.144 ohm per phase. Got it? So that is then therefore we can also get synchronous reactance. So that's why in question here, hello. What is asked? Find the synchronous impedance and reactance. Actually, there should be an end, impedance and reactance of alternator which give the field current, produce a armature short circuit current and EMF in open circuit condition. So ISC and OSC is given. Okay, resistance is given, then this is the synchronous resistance and synchronous reactance we have to find out. Okay, so this is how we calculate, you know. So this is ZS square minus RA square, okay, because synchronous impedance diagram. Now this is 0.144 whole square plus minus what is the resistance? 0.1 whole square root of this. Okay. Root. It comes again 0.1 only. 104 you write, okay? Per phase. So when you use a phase values, so you get a per phase also this. Now, now we can calculate. Now we get this equivalent circuit parameter. Okay, for alternator. Hello, you know, per phase values. Here it is your E, induced voltage. Then this is your resistance, synchronous reactance. Okay, dear. And this, if load is put here, it is alternator. So we have a electrical load. Okay. So this terminal voltage is suppose V. Okay. Synchronous reactance, resistance, armature resistance. And here it is a load current or armature current. Okay. Armature current or load current. So again, this load parameters are given. My dear, what is the load condition now? What induced voltage must be on alternator be excited? It is deliver a load. So here load is given, load current. What is the load current is given here? 100 ampere. At power factor, at 0.8 power factor, means cos phi is given 0.8. Then we can calculate a sin phi also. Hello? Your sin phi will be 0.6. Okay? Then is with terminal voltage. This voltage is 200 is given. Okay? So V is given 200 volt. But again it is a line voltage. Okay? Volts, and it is a line voltage. So please you convert into phase voltage. So this V phase,
115.47.
very good. So this volt per phase value we can calculate.
3 से फिर divide होगा.
Yeah, divide by √3. Not 3, it is divided by √3.
115.47.
Very good.
बट ये 3 फेस का रहेगा ना सर? इसको फिर
No,
okay.
200 divided by
Got
this visual. Now, my dear, for this now we have drawn this earlier I show you at lagging power factor. What is your diagram? See, this voltage we consider as a reference value. Okay, see here, this is your voltage is, it is a V. Okay, V at 0 degree. Okay, now at lagging power factor your armature current is lag. This is your armature current. It lag by phi. Hello, my dear, you can calculate now this cos phi is 0.8, then phi equals to cos inverse 0.8. You get a 3687 degree. Okay, so this is the phi, and this is your V. You know, this is your V. इसको लार्ज करता हूँ मैं थोड़ा सा. This is your V. Then you know, due to this current drop in resistance here and here, there is a drop. So always a drop in resistance in phase with the current. ये current के this is armature current. So your drop in resistance, it is parallel to current. Okay, so this will give you IA RA. And drop in reactance, it is perpendicular. It make a 90 degree here. So this is IA XX. Now this plus this, okay, this voltage and this drop, it will give you here, it is induced voltage E. Okay, so he is asking this E voltage. Okay. Okay. Now this is your V. Yeah, this is your E. Okay. Now we have to actually we draw the big triangle, extend this. Okay, and we get this here. Like this is 90. Yeah? Hello. So this this V take here. Oh, hello, from here to here. we take a horizontal component of this V vector. It will give you V cos phi. And you know this is IARA. And if we draw the vertical component here of this V, we take this V is this side and V this side, horizontal and vertical. So this is will equals to this here, this part. Because so here this will give you V sin phi. Okay, so here to here and here to here. Got it? Hello, in this now in triangle O, A and B. Okay. So from triangle OAB or in triangle OAB, okay. In this right angle triangle OAB, OB square equals to OA square plus AB square. Correct, no? It means this is the E square equals to OA means V cos phi plus IARA whole square plus V sin phi exactly whole square. Now E equals to, if this square is removed, then there is a root of this, and this sorry. All right. Root square. This is at lagging power factor. At leading, na, this minus sign will come. Okay. So here he is asking only for lagging. Then okay. Now you put the values here. All the values. V is come here 115.47. Just 11.47 115.47 into the cos phi is 0.8 plus IARA current is no. What is the current? Now load, you take a load current, my dear, okay? 100 ampere and it is per phase. Here line current equals to phase current. So it is per phase. Here we taking all the per phase values. Okay. 100 into resistance is 0.1. This whole square of this plus V is again 115.47 into sin phi is 0.6 plus IA is again 100 and the reactance will come 0.104. Correct, no? Yes. This square also. The root of this. Okay, so he is only asking this E. But if voltage regulation, you can also calculate the voltage regulation. Now see, this will come 115 into 0.8. 92 plus it is 100.1 means it is 10 plus 10 also. So here first part, this become 102.37 square plus what is the value of this? 115.47 into 0.6 plus 100 into 104. Sorry, 0.104. So my dear, this come total
79.68.
again this whole square and root of this. So here this is square plus 102.37 whole square root of this. My dear, it comes 129.73 volt. It is a per phase. Now for 3 phase, root 3 of this into root 3. It will give you 224.669 volt line voltage. This is the here it is a 200 voltage line voltage. Here it is a, now your regulation is also find. Hello, per phase value you put in regulation, okay? But here it is not asked. If they ask, you can put the voltage, percentage voltage regulation will be E minus V by V into, either you put a line values and this, okay? So here it is not asked, but you can calculate minus, if you put a line values or either phase value you take, but both should be either line value, either phase values, okay? Divide by with respect to rated voltage. So this is your voltage regulation here. %, it comes 12.35% voltage regulation, okay? But here it is not asked, they can ask. So this is the method. Now this is the fourth step. Fourth, fifth. Now we can calculate. This is your fourth steps. Okay. Hello. This will be your fourth. We find then fifth. You can calculate the voltage regulation. Okay. So these are the steps of your voltage regulation by indirect method.
तो इसको भी शेयर कर देंगे.
कोशिश आई एम ट्राइंग है, बट ये रीडेबल होना चाहिए ना. Okay. Excellent. Okay, dear. So now evening, in evening there is a class. Then see, this is complete now. No numericals are remaining here in this. Now in evening we discuss the remaining questions here from your ETO set, na? Chapter wise here. So some question already taken care, but like Drup setting and these things we cover, and we also discuss this power system. So mostly in the evening we complete the 6th chapter also, this neutral earth resistance fault calculation. Okay, then tomorrow Sunday I want to discuss the rectifier, this chapter rectifier, because lot of questions from rectifier also. Okay. Okay, dear. Okay. Okay, dear. Now I'm ending the session. Okay.
Thank you, sir.
Yeah.